Hello, everybody. We're live. Happy, what is it, Thursday? I don't know about you, but I tend to lose track of the days from time to time. I hope everybody had a nice Easter weekend, as good as you could possibly make it. I had a good time. Nice to see you. Thank you for checking out the stream. We got a few people today. Today's stream is our first one in over a week, so it's kind of exciting to be back on and to keep it going, to keep talking about space. I felt the last couple weeks we did a lot of freeform stuff, and so this time we're going to do some more focused things. We got a couple of news items we want to talk about, but then we're going to dive into the planets. We're going to start with our solar system, and we're going to start with, tonight, just the inner planets. Mercury, Venus, a little bit on Earth, and Mars. 4 very interesting places, 4 unique places that we're going to talk a lot about. As always, we're going to take questions, so please ask lots of great things. I am an open book about any topic in astronomy, and even if we're in the middle of one thing, I'm happy to divert to something else if you're interested in that. So we'll have some fun with that. A couple of things, a couple of news items. We changed things up a little bit. We lowered the resolution of the stream to try and get it to be a little bit more consistent. And unfortunately, it's already telling me that it's not being consistent, but that's okay. We're going to do our best. We're going to have some fun. We're going to see some really cool things, and we're going to practice until we get it right. Okay. So the first thing we're going to start with today is this comet. Now, I don't know if you've heard much about Comet Atlas. We've talked about it a few times over the past few weeks. And I often show this site here. So Comet Atlas, and we'll start at the top. This is kind of the path that it's taking as it works its way around the sun. And you can see it's gotten pretty close to where the Earth is. There's the comet right there, and there's our Earth. Well, you might have heard in the past week there was some words about, oh, maybe the comet is breaking up. Maybe it's not going to survive. Maybe it's disintegrating. Well, as it turns out, that's exactly what's happening. Now, you can see this is the brightness curve of that comet. So basically, it measures the brightness day by day by day based on observations of big telescopes, science-based telescopes, right? And so what they're doing is they're looking at how bright is the comet, absolutely, over time. And based on how bright it gets, you can predict how bright it should get as it gets closer and closer to the sun. And so one of the things that happened was the comet, we were expecting it to get really, 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 really bright. All these dots here show that in February and March it brightened, it brightened, it brightened. It was going to go all the way up to where this gray line is here. That was the original projection of a magnitude of minus 0.5 or minus 1, which is brighter than most stars in the sky. So this would have been a really spectacular comet to look at. A really spectacular comet. But unfortunately, that didn't happen. About a week ago, there was some words about, oh, it broke up a little bit. The brightness curve kind of stalled, and we thought, okay, maybe it's going to survive. Maybe it'll be okay. I did a stream with the Royal Astronomical Society of Canada last Wednesday, and one of the things that we took a look at was this picture right here. And this was 2 different pictures of the comet, Comet Atlas. And one of them was about, I think, 3 days before the other one. So in the first picture on the left, you can see that the comet looks pretty close together. The nucleus of it looks pretty normal. It looks, I guess, what we would expect a comet to look like. But on the right, you can see that it's starting to fatten a little bit. It's broadening out. It's changing a little bit. And so we aren't quite sure what that means, or at least we weren't a few days ago. But now things have changed a little bit. And since that picture came out, we've gotten a much more clear view of what's happened. Here's a lovely little GIF image. And if you look closely, you can kind of see that there's not just one big clump. The Astronomy Picture of the Day is a very well-known publication, day by day, of a great image in space. And today, they actually posted a really fascinating picture. I'm going to show it to you now. And this is going to show you definitely. This is today's Astronomy Picture of the Day. You can actually see that there are several pieces of this comet. 1, 2, 3. I count 4 distinct pieces. That means this comet is in fact breaking up as it's heading in closer and closer to the sun. Why does that happen? Well, we're not really sure. I mean, comets are big, dirty snowballs up in the sky, right? And so as it gets closer and closer and closer to the sun gets hotter and hotter and hotter, of course. And the pressure on the comet, the pressure on the ice, gases in the comet can escape and blow it to pieces. And so there's a lot of different things that can cause it to break up, but it seems to have actually happened. And that does explain the brightness curve that we saw a little bit earlier. That does explain why it's not getting any brighter, it's starting to get dimmer as pieces of it start to break up individually. And so what is likely to happen over the next few days, weeks, as it gets closer to the sun, it will likely reach its closest point to the sun where it will disintegrate completely and just become a stream of water vapor, dust, gas, whatever's left. It won't be bright, we won't be able to see it, and that will pretty much be the end of Comet Atlas. Now, there was a lot of excitement about this comet because we thought, well, you know, it's really brightening really fast. It could get brighter than any stars in the sky. That would be an amazing thing. But unfortunately, it's not that likely to happen, especially at this point. It's not going to happen. And it was actually thought, somebody published a quick article about this comet might have actually been a fragment of an older comet from about 150, 200 years ago. And so that comet, as it came around the sun, a chunk of it may have fragmented off, and that's why this comet has come close now, and because it's a smaller piece, it's disintegrated even further. So this is not uncommon. In the past, I think the last time I did a show, we talked about Comet Ison, which 5 years ago was supposed to be this like comet of the century. Again, we say that often. And as it went around the sun, it disintegrated and we never saw it again. So it tends to happen more often than not. But hopefully we get another one like the Great Comet back in 1997, Hale-Bopp. That was the comet of the century, and I hope that we get a better one than that, because that would be pretty amazing. So this is kind of what's left of our comet. The brightness curve is totally shut down. Not much left. And even in the GIF, you can see fragments of it. So unfortunately, the next few weeks, the comet's going to get dimmer and dimmer and dimmer and not be that nice. And, well, that happens. Like I said, it's a pretty common thing. So to our main stories of the evening, we're going to talk about the inner planets. And like I said, I'm just going to keep talking about all the cool things that I know about our inner planets and why they're so special and why they're so interesting. But please feel free to ask questions. In the chat, if you want to say hi, let me know you're here. That'd be really awesome. That said, I'm happy to talk to the ether and just kind of do my own thing, because the reason that we're doing all this is not to make money. It's really just to make friends and talk more about space, because that's really what I love to do. And every week that goes by that I can't be out in my planetarium talking to people about space, I get to talk to all of you lovely people who tune in about space and do that thing that is my passion. So we're going to get to it, and I'm going to start off, of course, with our Universe Sandbox, because this is a great little program. I've shifted things a little bit. Oh, hello, Charmin. Nice. Thank you for saying hello. Thanks for tuning in. Nice to see a hello there. So this is our Universe Sandbox. We're back in here, and I decided to show our inner planets. We're going to come back to this every so often. Let's speed it up a little bit, at least as fast as we can go in the simulation. So Universe Sandbox, again, I'm not affiliated with them at all. It's a program that I paid for that is really, really fun, really great to use, and lets you do fun things like smashing stuff together. I just think it's a really great program if you love space and want to play with things. And they've done some really great work on this program. So we're going to use it to take a look at our inner planets. And of course, we're going to start with Mercury, the closest planet to the sun. Mercury here, I actually brought up, I shifted the image a little bit so we can take a look at the stats on some of these planets. And so it might be a little bit difficult to see some of those numbers. I know we are running in 720 and maybe lower quality, so I will read things out as we kind of go through it all. But Mercury, of course, is the closest planet to the sun. You can tell by the orbit that it goes the fastest. I don't know if you realize this, but when you look at our solar system, the general rule of thumb, and because of the way gravity works, is that planets closer to the sun orbit faster. Planets closer to the sun orbit faster. And that's basically just because they have less distance to cover. right? They're closer to begin with. They fly around a little bit faster. And Mercury takes just 88 days to work its way all the way around the sun. We can see here 87.9 days, right? Close enough. And it's only, it's pretty close, relatively speaking, to the sun. Still about 50 to 70 million kilometers, which is pretty big. Pretty far, right? Pretty far away, considering our moon is about 384,000 kilometers. So Mercury's pretty far away, but it is the closest planet, and it's so close, it is just baking under the power of the sun. So let's go start a new animation here, and we're going to bring up Mercury, closest planet to the sun. Here's what Mercury looks like. We're going to bring up some better lighting so we can take a look at it. Mercury is a lot like our moon. It looks a lot like the moon. It's a little bit more golden. It's got a lot of those craters, right? Back in the early solar system, after everything formed, for about 2.5 billion years, there was this period of bombardment where all the leftover rocks in the formation of the solar system smashed into things. And a lot of them, that material was stuff that the sun, that didn't become part of the sun, rather. So all that other material just kind of kept flying around and smashing into different things. And so Mercury was, of course, one of those things, being a planet. And because Mercury has no air around it, it has no atmosphere, it has not really much else to offer, no water, possibly a little bit of water in some of the craters on the South Pole, but very likely no major amount of water, no chance for life. Mercury is basically a giant ball of rock and iron. And all that's left of it is these craters and this very hot surface. Now, one of the interesting things about Mercury is that because it has no atmosphere, its surface temperature actually varies a little bit. So you see the average surface temperature here is 152 degrees Celsius. Now you might say, well, that's pretty high, but seems kind of low, right? Water boils at 100 Celsius, so 150 is not that much higher than boiling water. Why isn't Mercury hotter than that? And the answer is because this is an average. Daytime on Mercury is really hot, about 350 degrees Celsius. 350 degrees Celsius. If you want to do turn it into Fahrenheit, you double it and add 32. So about 732 degrees Fahrenheit on the surface of Mercury. But we stick to Celsius here in Canada. So 350 degrees Celsius in the daytime, but then when it gets dark at nighttime, when the sun is not shining on the surface of Mercury, the temperature plummets down to minus 170 degrees Celsius. So in daytime on Mercury, 350 degrees. Very, 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 very hot. Nighttime on Mercury, minus 170 degrees. Really, really cold. And so you say, well, how's that possible? It's just so close to the sun. Shouldn't it be hot all the time? And the answer is no. I mean, that Mercury has no air around it, has no atmosphere. It's basically barren and exposed to outer space. So when the sun shines on it, yeah, the sun heats up the surface a lot. But on the nighttime side, when there's no sunlight, all that's left, there's nothing to stop the surface of Mercury from being exposed to the vast, dark, and cold of outer space. And sure enough, space is pretty cold, right? Minus 268 degrees Celsius on a normal day. So Mercury's pretty chilly. One interesting thing about Mercury, and this doesn't actually capture it properly, I'm going to point you to the top right-hand corner of our screen. Mercury's inner composition is really amazing. Now you might think that, okay, it's a rock, right? It's just like the moon, but the really amazing thing is that 85% of Mercury's core is solid iron. Basically, Mercury is a giant ball of iron surrounded by just a little thin, I say thin, but 400 kilometer thick layer of rock. Now this is much bigger, comparatively speaking, than the core of Earth, the core of Mars, the core of Venus, right? Lots and lots and lots of iron. And so, relatively speaking, 85% of Mercury is a solid ball of iron in this thin layer of rock. I'm going to bring in a couple other things so we can actually do some comparisons here. The first comparison, of course, is to Earth's moon. And you can see that, let's put it to still. So we'll I'll move it over a little. Oops. Ah. Okay, so I may have destroyed Mercury. That's okay. Delete. We can always fix that, and this is one of the nice things about Universe Sandbox, is it can be fun to destroy stuff too, right? So there's the moon and there's Mercury, right? Not very different, a little bit different in their mineral composition, right? The moon's got some of those darker lava plains. It didn't cool as quickly, and Mercury, on the other hand, a little bit bigger, basically baked by the sun for a long period of time. The moon did form a little bit later because it kind of ended up forming from a collision with the Earth. So Mercury was around a lot longer, a few 100 million years longer, right? And then, of course, if we bring up the Earth, we can see that the Earth is quite a bit bigger than planet Mercury. Mercury is the smallest planet in our solar system. Previously was Pluto, and we'll eventually get to Pluto a couple episodes from now, I'm sure. But for now, Mercury is the smallest planet. In fact, I've said this before, but there are actually 2 moons in the solar system that are larger than the planet Mercury, which is kind of amazing to think about. The first is Titan. So there's Titan. Let's get rid of our moon and move them over so we can just kind of do a size comparison there. So here's Mercury, and there is the moon Titan. Titan is the moon of Saturn. It is the second largest moon in our solar system. The largest moon in the solar system is Ganymede. There they are there. Ganymede is the moon of Jupiter, and really there's not a huge difference between them, right? There's not not a huge size difference. So Ganymede's a little bit bigger, Titan's a little bit bigger, Mercury quite small, quite rocky. Question from Charmin in the chat: is Mercury really that round? And the answer is yes. Most of the planets are spheres. They're ball, right? They're spherical. They're round, and it has to do with gravity. Gravity wants to pull all of the stuff that's collected together into the center of the object, and because things they start out rocky, basically, let me back up a little bit. When the solar system formed, you have the sun forming in the center. It's bigger, it has 99% of all the stuff that was in the birth cloud of our solar system, all crammed into the sun. The leftover 1% was flying around it like a giant frisbee of rocks and dust. That dust collected into rocks, the rocks collected into boulders, the boulders collected into mountains, the mountains into giant small moons, and the moons into planets. That's how things basically formed, gradually over time. And the biggest things started to sweep up all the extra stuff. So originally, planets like Mercury and even the Earth were big clumps of different sized rocks. But because they're so big and the collisions are so powerful, right? Like we throw stuff here together all the time, right? If we throw a moon at the Earth, and all these moons at the Earth, right? They make heat. It gets really, really warm. And that heat causes all these rocks to become molten, and they start to melt together, and that's when gravity takes over. Now when you have a liquid, gravity can pull things into a very nice sphere. And so that's basically what happened, is all these rocks smashed in together, generated a ton of heat. They heated up. All the planets were molten back then, at least all the rocky ones were these molten chunks of iron. And the other thing that happens when they're molten is that more of the heavier things sink down toward the center. So that's why all the iron that was in those rocks that formed the planets, all that iron sunk down to the core. And then the lighter stuff, the rocks, dust, sand, eventually, and water goes up to the top, right? That's just because of density and buoyancy, all right? And so the long answer to your question, Charmin, Mercury is really that round, and it's that round because of how it formed. Eventually, over time, it did cool down, but again, most of its core was this solid iron. So let's say goodbye to the Earth there, and let's take another look at Mercury. Mercury is not a terribly interesting planet. I mean, it's very straightforward. Oh, it's running away from us. It's very straightforward in that it is a rock. It's a big ball of iron covered in rock, right? So not that interesting. It can't support life. It's too close to the sun, which means lots of dangerous radiation, lots of the sun's heat in the daytime and cold in the nighttime of space. And so there's not really much else that you can say about Mercury. The Messenger spacecraft is a very famous one that visited Mercury over the past decade and mapped the surface. So this is an actual map of the surface of Mercury, and you can see that it's got some bigger craters and some smaller ones, some different minerals, different sizes, different compositions. It's got one really big impact crater at the bottom, at the South Pole. But other than that, that's Mercury in a nutshell. Not too much to see. Now there was, like I said, I alluded to a little bit earlier, there is a little bit of water, potentially, in some of the craters on Mercury that never see sunlight, right? Some of these craters are so deep that they can never actually fully get exposed to sunlight, and so they actually can have a little bit of ice water in there. Okay, so that's Mercury. Like I said, I will take other questions as we kind of go through things, but without further ado, we're going to move on to the planet Venus, and I'll leave Mercury up for a sec because Venus, as we said, it's quite a bit bigger. There's Venus compared to Mercury. Select Venus there. Whoop, that's better. So you can see Venus quite a bit bigger, and Venus is often called Earth's twin. Earth's twin, and you can kind of see why. Venus and Earth are about the same size, pretty almost exactly. Like Venus's radius is 6,052 kilometers. Earth's radius is 6,371 kilometers. So that would make Earth about 650 kilometers wider than Venus at the equator. Not a big difference, right? However, their formation has a very big difference. And if we go back to our solar system from earlier, I've got to find which one I was going to. Yeah, this one here. So let's bring up our solar system from a little bit earlier. All right, we can see Mercury very close to the sun, Venus closer to the sun than Earth. And so it had a very different history. One of the things that we can bring up that I've done in the past is the habitable zone of our solar system. Just to refresh, the habitable zone of our solar system, the red is basically where the sun's energy is so hot that any water would evaporate into water vapor. So you can't have liquid water. The blue zone is where it's too cold and water would freeze into ice. So it's too cold. The green zone, known as the habitable zone, is the place where you can have liquid water, where the sun's energy, the sun's radiation, is not so high that it causes all the water to evaporate, and not so low that all the water freezes. It's just right for liquid water, which is, as far as we know, the major component for life. You need water for life, at least as far as we know. And you might notice that Venus is just outside of the habitable zone. Earth is just inside the habitable zone, thankfully. And Mars is just on the outside a little bit. Now, one of the other things that's happened is that over time, the sun is actually getting hotter. So a few million years ago, or a few 100 million years ago, the habitable zone was closer to the sun. This green zone, Venus was actually within the green zone. So a long time ago, it's thought that Venus might have been a life-bearing planet. It might have had trees and oceans. Maybe life, I don't know. But it might have at least had oceans of liquid water and a much nicer atmosphere. Unfortunately, today, Venus is a lot different. A lot more dark and depressing. Well, not dark, but bright. Very bright, but pretty depressing. So let's go take a closer look at Venus. Again, we're going to bring up the Earth so we can show it for comparison. Now Venus, what you're actually seeing right now on Venus, as I crash them together. Okay, let's, yeah, they're doing their thing over there. Let's try that again. And I'll actually remember to press pause this time. There we go. So we pause it this time. We've got Venus again. Very common, I guess, normal looking planet. But one of the things that you see on Venus when you first look at it is clouds. This is not the surface of Venus. It's not the surface at all. We got a question in the chat from Sebastian. Why doesn't Mercury have an atmosphere, for one? And why is Mars red other than iron? So a two-part question. The first part, why doesn't Mercury have an atmosphere? The answer is that if there was an atmosphere on on Mercury, atmosphere is made of particles, right? Oxygen, nitrogen, carbon dioxide, and they're all moving around. They're all bouncing all over the place. And gravity from the planet is what holds them to the planet. So two things about Mercury. The first is that it's very small. It doesn't have as much weight as the Earth or Venus or Mars, or especially not Jupiter or Saturn. So it doesn't have as much weight. And two, because it's so close to the sun's light heats it up, heats it up, heats it up. So if Mercury did ever have an atmosphere, for one, it wouldn't have as much gravity to hold on to that atmosphere. And for two, all that sunlight would cause those little particles in that atmosphere to speed up and jump away from the planet. Okay, so basically the atmosphere, if there was one on Mercury, it would get boiled away and we would never see it again. So that's the first part of your question. Why doesn't Mercury have an atmosphere? The second part, why is Mars red other than iron? I will bring up Mars as a teaser right now. It's pretty small. Mars's redness is entirely because of iron. It is entirely because of iron. It's called iron oxide. Right? When iron oxidizes, that's basically a fancy word for it rusts. When you see rust here on Earth, that's the exact same thing. Okay, so Mars, the soil on Mars has a lot of iron in it, and there was at one time a lot of oxygen on Mars, and that oxygen oxidized all the iron, so it rusted. Now the amazing thing is that that's only on the surface layer. Only the thin top layer of soil on Mars is red. If you look at some of the rovers, Curiosity actually is the only rover that's drilled into the surface of Mars. When you look at where it drills in, the dust that comes out of it is not red. It's like a brown sandy color. And that's because the rocks on Mars are actually kind of the same color as rocks everywhere else in our solar system or on Earth. They're gray or brown or sandy. So if you took a giant broom and dusted away that top layer of Mars's soil, there's no more red. There's no iron. It's just earth-colored, soil-colored, brown, gray, sandy. Okay? So the only reason Mars has that red soil is because the top layer of it has a lot of iron in it, and that iron oxidized or rusted a long time ago. So thank you for the question, Sebastian. All right, so back to Venus, though. What we're looking at right now is the surface of Venus, the clouds in the atmosphere, right? Venus has thicker clouds, thicker atmosphere than the Earth does. And it's mostly made of carbon dioxide, the same stuff that's in our atmosphere that's causing it to heat up. Except on Venus, there's so much carbon dioxide that very little heat can escape. And if you combine that with the fact that Venus is really, really, really close to the sun, well, at least closer than the Earth, it gets hot. Venus is the hottest planet in our solar system. All right, I'm going to bring up Venus. This is Venus without its clouds, by the way. Venus is the hottest planet in the solar system because of its clouds. Those clouds are so thick, like I said, they trap heat. The normal daily temperature on Venus is about 450 degrees Celsius, hotter than the surface of Mercury in midday. And so Venus gets really, really hot, but not only that, the atmosphere is so strong, there's so much of it, it actually weighs about 93 times as much as the atmosphere of Earth, which means that if you were standing on the surface of Venus, the temperature, or rather the pressure, is 93 times the atmospheric pressure on the Earth. That's like being a kilometer under the ocean. That's how much pressure there is. But the amazing thing is, people have sent spacecraft to Venus. Humans have sent spacecraft to Venus. And this is what the surface of Venus looks like. These images are some of the rare images of other bodies in our solar system. I think only 5 or 6 objects in our solar system have been visited by a spacecraft that has landed. Mars is, of course, one of them. Venus is one of them. Titan, the moon of Saturn, is one of them. And there's a couple more. One of them's in asteroids, maybe? You'll have to correct me if you know the answer to that. I'd love to hear it. So this is the surface of Venus, and you can see those yellowish carbon dioxide clouds, the surface with high pressure. There's no life on the surface. No life could survive that kind of pressure, the high temperature. It's at least not today. But maybe hundreds of millions of years ago, when Venus was not as hot, maybe its atmosphere was different, maybe it did have liquid water on the surface, maybe it could have supported life. But you can see now that it's just a rocky, barren place. And these spacecraft, the Soviet Venera landers, there were a few of them, but these two, they had to, as they were coming down through the clouds, take all the data they could, because they only lasted for about 45 minutes on the surface before they just kind of died, because the pressure and temperature were so great that there was no way for them to survive. So we're back in Universe Sandbox, and we're going to look at some of the stats, of Venus. So we talked about its radius. It's pretty close to the Earth in size, but there's that average surface temperature, 464 degrees Celsius. It's actually the closest planet to the Earth. It's closer than Mars, but we don't really go to Venus because of those thick clouds, right? Now, there's a couple interesting things about Venus that I always love to talk to people about. One of them is the fact that it actually rains acid on the surface of Venus. It actually rains acid. Now, I'm not correct in saying the surface. The upper atmosphere has clouds of sulfur dioxide. Sulfur dioxide can produce sulfuric acid. And so basically what's happening is in the upper atmosphere of Venus, it starts to rain acid. Except that acid never reaches the surface. As the acid starts to fall down through the clouds, it gets hotter, the pressure gets greater, and then all of a sudden those droplets evaporate and the cycle repeats. So it's like rain in the upper atmosphere of acid, but it never reaches the surface because it's just too hot. And so Venus, although it's named after the goddess of love, the surface is a lot more reminiscent of just a hellish environment, right? That this is a false color image, by the way, that I'm showing right now. It's from the Magellan probe. And it's false colored so that we can see a lot of the surface features. It's thought that there are active volcanoes on the surface of Venus. So not only is the pressure extremely high, not only is it really, really hot, but there's also volcanoes, just to add some more flavor to this lovely hellish planet that we have here. So that's kind of Venus in a nutshell. We have sent orbiters and landers to Venus, as I said, and I think the most recent one was the Akatsuki probe from Japan. One of the amazing things about Venus is that we could actually live there, believe it or not. Even considering all the crazy stuff I just said about Venus, we could live there. And the reason is that in the upper atmosphere of Venus, if you're only a little bit into the clouds, not very deep, a few kilometers, the temperature is about 20 degrees Celsius. And yeah, I know it's acid rain up there, but if we had these big balloons that could survive in those clouds, they could float, and we could live inside these giant balloons on Venus, where the temperature would be a nice, balmy 20 degrees. Pretty amazing. Of course, you'd have to worry about the fact that it's 400 degrees below you and much deeper and denser and nastier than our ocean. But still kind of cool to think about. One of the things about Venus that's been looked at for a long time, famous scientist Carl Sagan, he would think that these darker regions on the clouds of Venus, you can actually, it's kind of hard to see them right now, you can kind of see some darker spots, but if you look at some images of the clouds of Venus, those darker parts absorb more heat, right? Darker colors absorb more energy, more heat. They reflect less light. And so even though the clouds of Venus are quite reflective, darker regions can actually absorb more of that light. And Carl Sagan thought that, wouldn't it be amazing if those darker regions were actually bacteria? These dark, big clumps of bacteria that were living in the atmosphere, absorbing all the radiation from the sun and actually heating up the planet in the process. It is possible, it is a theory, hasn't been proven yet, but kind of cool to think about. That A, there might be a place that we could live on Venus, and B, there might be life that's still there. These extremophiles, right? Extremophile life is life that can survive in extreme conditions. On Earth, that means near volcanoes or inside volcanoes. It means within deep underwater vents. It means in icy cold rocks and chunks of ice. We found life in all of those places on Earth, and so why not in these other places in our solar system? So that's Venus in a nutshell. A couple other one of the other interesting things about Venus that I love to talk about, I'm going to go back to our solar system for a second so we can actually see it. Where is it? Moons and large objects. Okay. We're going to load up our solar system. So Venus, oops, that's the sun. We don't want to go that close. Let's speed it up a little bit. So Venus actually orbits the sun in, I believe it's 250 days, give or take. Let's take a look. Its orbital period, 225 days. Oh, okay. I always get this wrong because the really fun thing about Venus, and I'm going to see, there it is. Okay. So I want you to look at the rotational period. That's the time it takes to spin, or what we call the day, right? A day on Earth is 24 hours. A day on Venus, the time it takes to spin, is 243 Earth days. It spins really, really slowly. And the time it takes Venus to orbit the sun, an orbital period, its year, is only 225 days. So what that means is that a day on Venus is longer than a year on Venus. A day on Venus is longer than a year on Venus. And not only that, Venus actually spins backwards. Most of the planets in our solar system, I should say all the planets, except for two, Venus is one of them, all the planets, as they orbit the sun, they spin, I guess from our point of view, that would be counterclockwise as they orbit the sun. This is just a natural way of rotation. Venus spins in the opposite direction. It spins what we would see as counterclockwise right now. And we don't know why, but the leading theory, and as is the case with most theories of how planets in our solar system got their little quirks, is that in the early solar system there were so many rocks flying around that maybe Venus got hit by a rock so hard that it actually spun it backwards. And that's the leading theory. That would cause Venus to spin very slowly. If it got hit just at the right angle, it would spin backwards. And that's how we can reproduce the way Venus is behaving right now. So that's Venus in a nutshell. There we go. Again, so I just want to say to everybody, thanks for tuning in. We're still going to keep going a little bit. We still have to talk a little bit about the Earth and a little bit more about Mars. But I just wanted to remind everybody that there is a lovely chat there, and I would love to have some other questions from you. We got a couple already from Sharon and Sebastian, so thank you for asking those. It doesn't have to be just about planets. We can talk about anything, but today we're focusing on our inner planets of the solar system. Okay, so we're going to go back to our universe sandbox, and I want to talk a little bit about the Earth. Not a lot about the Earth. I mean, we know quite a bit about the Earth. I mean, it is the planet we live on. It's a nice, comfortable temperature. You know, it varies a lot. Right from the poles, it can get down to minus 80 degrees Celsius, and at the equators, it can get up to plus 30, plus 40 degrees Celsius at the equators. But the average temperature of the Earth is quite nice, quite balmy. Earth's average temperature is actually about 14 degrees on the surface, which is nice, right? And it varies season to season. We have the Earth is tilted 23.5 degrees, and that gives us the seasons. At different times of year, different parts of the Earth get more direct sunlight. So right now we're in North America, where I am in Toronto. In Canada, we're in springtime. We're slowly working our way into northern hemisphere summer, and that'll be winter in the southern hemisphere. The Earth is the biggest of our rocky planets in the solar system. We're actually going to bring up a new thing so we can take a nice close look at the Earth. There it is, spinning around. It's getting a little bit colder here because we took away the sun, and without the sun, the Earth would slowly start to freeze. So we're seeing it freeze. But Earth is a planet that is abundant with water. It has liquid water, and it has lots of life. Life covers the entire surface of the Earth, with a few exceptions. I mean, the poles are very icy, but there is life in ice. The oceans are very blue and wet, but there's tons of life in the ocean, maybe tons more than on land. And we've got these land masses. Earth is often called the blue planet because it's covered in about 70% ocean. Lots and lots of water to look at, right? Especially the Pacific Ocean. Not as much land, yet still the largest of the rocky planets in the solar system. The really special thing about the Earth is the moon. And if we actually bring up the moon, we'll set the moon to orbit so it's not going to destroy the Earth, and we'll actually give it roughly the right distance. 384,000 kilometers between the Earth and the moon. Our moon is actually pretty big compared to the Earth. It's pretty big compared to the Earth. By the way, Mercury and Venus don't have any moons. Okay, they don't have any moons. They weren't big enough to capture any moons. And yet Earth has this moon that's decently sized. Our moon is about a quarter of the size of the Earth. Try and bring it into frame there. About a quarter of the size of the Earth. And that is surprising. Most moons are much, much smaller. When we get to Mars, we're going to see that Mars, its moons are really tiny compared to the size of the planet. And even our moon is, I think, the 5th largest moon in the entire solar system. So even the really big ones, like I said, Titan, Ganymede. I think what else is a big one? I think Europa's pretty big. Yeah, Europa's bigger than the moon. Than Earth's moon. Oops. There we go. Europa's pretty big. What else? Io. Io's a little bit bigger too, right? So these are all giant moons in our solar system that orbit the biggest planets, Jupiter and Saturn. And if you look at, how large Jupiter and Saturn are, right? We know Jupiter's so big you can barely contain it here. And Saturn also pretty huge, right? So these planets are gigantic. So of course they're going to have big moons. But our Earth, relatively speaking, a lot smaller, but still has a pretty big moon. Now why is that? Well, we got another question in the chat from Vicky G. Thanks for tuning in, Vicky. Why are the inner and the outer planets separated by an asteroid belt? And how did this asteroid belt form? Thank you for asking that. Let's take a look. Let's bring up our solar system. Now we can represent the solar system pretty well. You can see a lot of the asteroids here. The asteroid belt, by the way, is between Mars and Jupiter. So there's Mars right there, and here's Jupiter down here. So there's this region between Mars and Jupiter where there are a lot of rocks, about 100,000 fairly large rocks. And I say fairly large, I mean, 5 kilometers across or larger. So 100,000 to 300,000 rocks. Now, if anybody's seen those cool space fighting movies, right, like Star Wars or Star Trek, often when they represent a big clump of asteroids or an asteroid belt, they're everywhere. Right? The heroes have to venture through the asteroids very, very carefully so they don't hit any of them as they're working their way through. And often there's a chase as well. So, they'll dodge one asteroid and one of the enemies smashes into it, never to be heard from again. Unfortunately, the reality is that in outer space, asteroids are really, really far apart. If you were close to one of the asteroids in our asteroid belt, like Ceres, the largest one, if you were on Ceres, which is actually now been upgraded to a dwarf planet, by the way. There's Ceres. Well, a little fast. Ceres is a dwarf planet now, but if you look from Ceres, it's kind of hard to see any other asteroids. Like if we actually take a look and get rid of the labels and the trails, it's kind of hard to see other asteroids in the sky. You can see a few rocks out there, but it's not like they're close enough together that we're going to smash into them, right? So in space, the asteroid belt is actually pretty spread out. Okay. But why is there an asteroid belt? That was the question. Why do we have an asteroid belt? And the answer really has to do with Jupiter. Jupiter is the biggest planet in the solar system. We'll probably talk more about it in the next episode when we talk about the outer planets. But Jupiter is kind of the shepherd of our solar system. It's really big. It's if we bring it up again, let's start a new simulation, and actually we'll take a look because here we have the Earth. We're going to pause it so nothing gets destroyed yet. There's the Earth, there's Mars, and then we get to Jupiter as well. There, see, Jupiter's much bigger. So Jupiter also has a lot more mass. Jupiter is bigger and heavier than all the other planets combined. Okay? So Jupiter's got a lot of gravity. And what that means is that Jupiter can destroy things. It can capture things. In fact, Jupiter has 79 moons, and it's thought that most of those moons are captured asteroids that may have crashed into the Earth and destroyed the Earth, but they didn't. Jupiter's gravity held on to them and kept them, captured them as moons. Okay, so Jupiter has a lot of gravity. In the past, we've talked a little bit about this thing called the tidal force, where when something's orbiting something else, it pulls a little bit harder on one side than the other. What I mean by that is if you look at Mars and Earth, if you imagine they were this close together, Mars's gravity is pulling on the right side of Earth a little bit harder than the left side. And that creates a difference in gravity that we call the tidal force. This difference in gravity can actually shred planets and moons and asteroids and everything. So the idea is this, and the leading theory about our asteroid belt is this. In our solar system, there used to be a planet. A ninth planet. And not like Pluto, and not like this weird planet 9 that's way in the outer solar system, but a ninth planet between Mars and Jupiter, somewhere out here. That ninth planet couldn't survive for very long because Jupiter's gravity slowly shredded it with the tidal force. And all those little bits that were left over from that planet were pulled apart and left spread out in the graveyard of our asteroid belt between Mars and Jupiter, where it remains to this day. If you add up all of the rocks in our asteroid belt between Mars and Jupiter, you would get a planet that is a little bit bigger than Mars. It's just not possible for it to stay together if it's there. I was talking about this with Jesse Rogerson a couple weeks ago as a guest, and one of the things we talked about was how all the planets in our solar system are in the best configuration. This is the maximum way to cram in 8 planets to a solar system. If you tried to put in another planet, it couldn't survive. It would get kicked out. Eventually, it would disintegrate. It would break apart or crash into something else. And so our solar system is stable. It's been that way for 4.5 billion years, and it's not changing anytime soon. So when another planet did try to form between Mars and Jupiter, it was shredded by the gravity of Jupiter. And that is the answer to Victoria's question. So thank you for asking that. How did the asteroid belt form? We covered that. Why are the inner and outer planets separated by an asteroid belt? Jupiter's gravity. Okay, so thanks for that question, Victoria. We have another question from Lauren. Has Earth always had only one moon? That's a great question. Earth, one true moon. When we talk about moons around a planet, we have to talk about natural moons. Okay, there's you might have heard a couple of weeks ago there was another moon, I should say, that was orbiting the Earth. Now it was really small. It was about the size of a car. Would you call that a moon? I don't know. Probably not, right? Earth's one moon is 384,000 kilometers away and about 3,500 kilometers across. So it's pretty big. Again, if there was another moon in there, it probably wouldn't be stable. Our moon is so big that its gravity would shred any other moons that came by. Now, it is possible for Earth to capture other rocks, and maybe a long time ago it captured a rock and had a second moon, but it would only last for a few million years before it would either get kicked away by our moon, it would disintegrate, it would kind of head on out. And so this tiny little car-sized moon that came by a couple of weeks ago was only, it was in orbit around the Earth, but only for, I think, a couple of days. And then off it went somewhere else in the solar system. It just wasn't stable. So as far as we know, Earth has always had just one moon. And it's always been this big moon. Now, how did it form? It's an interesting question. So let's just go. We got a couple more in chat. I will talk about how our moon formed, but so Lauren, has Earth always had only one moon? Yes, it has had only one moon, as far as we know. Some other ones have come in and out every so often, but they're usually just small rocks, captured asteroids, and we wouldn't call them moons, so to speak. Another question from Sebastian. What would happen if Earth's orbit just disappeared and it just floats off? We actually did this in an earlier episode, and I'll show it to you again because it's kind of fun. So we have our solar system here. Now I want you to take a look at all the planets. We'll go to Jupiter's orbit. That looks pretty good right there. Now here's what we're going to do. We're going to pause it. The reason that the planets orbit is because of gravity and momentum. The Earth is actually flying around the sun. It's actually being pulled toward the sun, but it's moving sideways so quickly that it keeps missing the sun, and that's basically its orbit. If the Earth just stopped its forward motion, it would fall directly into the sun, and that would be the end of it. So now what happens, though, if we get rid of the sun? There it goes. It's gone. We just deleted the sun. Watch what happens to all the planets. They continue in that same direction they were moving when the sun disappeared. So I think that kind of answers your question. Oh, you're welcome, Lauren. Thanks for your thank you there. But Sebastian, so what would happen if the Earth's orbit just disappeared and it just floats off? That's literally what would happen. If we deleted the sun, there's no central mass in the solar system to hold the planets in their orbits. And so they just all go flying off into outer space. And they'll probably do that for millions and millions of years until they eventually, hopefully, collide with something else. Let's speed up time a little bit. And there they go. The whole solar system flies apart. Even the outer planets, Uranus, Neptune, Pluto, dwarf planet, go flying out. Of course, the inner planets, because they're moving much faster to begin with, they orbit really quickly, they're all flying out in all different directions. For Earth, that would mean that no more life could survive on the Earth, and I say that truthfully because with no sun, no sunlight, it's going to get really cold really fast. And if we look at the temperature of the Earth right now, the average surface temperature of the Earth is now down to minus 143 degrees Celsius. So, yeah, space is cold, right? And so, Sebastian, to answer your question, what would happen if Earth's orbit just disappeared? It's not like the orbit would disappear, the sun would have to disappear, and that is what keeps the Earth in orbit. So when the sun disappears, the Earth stops its orbit and just goes flying off into outer space. Okay, so we're about 10 minutes out from the end of the hour, a little bit less than that. So I'm going to quickly go over the Earth and the Moon, and actually just start a new simulation here, see how the Moon formed. Basically, the short answer is something big smashed into it. Something the size of Mars, actually. A long time ago, a rock, and this is in the early solar system, maybe about 4 billion years ago, a rock the size of Mars, I'm going to pause for a sec, a rock the size of Mars called Theia crashed into the Earth. And we're going to watch that because collisions are fun. I'm going to slow it down. I'm going to pause it so we can slow it down a little bit more. There we go. We get to see this nice, slow collision. So this collision happened. When it happened, all the debris from this collision, the leftover rocks from this rock Theia, Mars-sized rock Theia, and the bigger Earth when it was younger, the leftover rocks started, these fragments, look at them, they're all named Fragment, that's great. They all started to fly around the Earth. And over time, they spun around faster and faster and faster, and gravity actually had them all collect into the Moon. Gravity pulls them all together, collisions pull them all together into our Moon. And a bunch of other rocks that probably crashed into the Earth and the Moon. But what was left over was a Moon. This doesn't simulate it very well, but it is kind of fun to see stuff crash into the Earth, right? So our moon did form, and this is the leading theory about how the moon formed. And the reason that this is the leading theory is that if you look at what the Earth's crust is made of and what the moon's crust is made of, because we actually have done that because humans have been to the moon, they're made of the same stuff. They have the same elements, the same radioactive isotopes, the same composition percentage-wise. They're made of the same stuff. And the only way that can happen is if they were born of the same thing. And so that's the idea about our Earth and moon forming. Now, with our last remaining time, I'm going to take us to Mars. For a question for the chat, you're welcome, Sebastian, for the answer. A question for the chat. I would like to ask you how the stream has been quality-wise. One of the things that we changed this week was that I actually lowered the resolution down to 720 because I wanted to get something a little bit more consistent. So just tell me offhand quickly, have you had any hiccups with the audio or the video? Have you had any trouble with the resolution? Has it been pretty stable? Just let me know. I'm actually doing another stream, a private stream on Saturday for a group of Girl Guides of Canada. And so I want to make sure that it's working really well so that when we talk to them, we have a good time. And same for all our future streams with you lovely people. So let's go back and take a look at Mars. And I'm going to bring up our solar system one more time to take a look at it. Mars is a fascinating planet, maybe the most fascinating planet in our solar system. It is known as the red planet, as Sebastian alluded to a little bit earlier with his question about why Mars is red. But Mars is in the habitable zone, just at the very edge of the habitable zone. So we're gonna bring up our habitable zone again. Oh, thanks for adding that in. Video, a couple people. So Jen had a couple of drops. Charmin had a video freeze for a second. 2 or 3 times is not bad. It's much better than it was last time, and Vicky's got no problem. That's great. Awesome. I'm really glad. I want to make sure that things look smooth at least so we can all enjoy ourselves. So let's take a look at Mars. You can see that Mars is at the edge of the habitable zone right now. Now, one of those things I said earlier is that the sun is getting hotter over time. Over the next 1,000,000, 100 million, 200 million years, the sun is growing hotter. And that means that the habitable zone, this green zone, the place where you can have liquid water, is actually slowly moving outward. And so early in our solar system, Venus was in that habitable zone and had the potential for life, right? It had liquid water, potentially. But as we go further along in the sun's life, now Mars, which used to be too cold, is now a place where you can have liquid water. And a couple things that we've learned in the past 10 years, Mars actually has flowing liquid water. Mars, about 250 million years ago, had as much water as the Atlantic Ocean on Earth. Can you imagine how much water that is? Like, look at Earth. There's the Earth. I gotta pause it so they don't crash into each other. And here's Mars. Okay, so Mars is a small planet, about half the size of the Earth. Imagine all the water in this Atlantic Ocean was on Mars. It actually led to an ocean on the surface of Mars across the northern hemisphere. The entire northern hemisphere of Mars was a giant ocean 250 million years ago. But it's not there anymore. Why not? What happened? Mars lost all its water. Not all of it, I should say. It's got a little bit left. Most of it is frozen underneath the surface. There is a little bit of running water. Something happened a long time ago to Mars. And it has to do with the fact that Mars is a little bit smaller than the Earth. A little bit smaller than the Earth. The main reason is that, on Earth we have this liquid core, right? If we bring up the Earth, we can actually take a look at its composition. And this really doesn't do it justice, but I'll maybe bring up a better picture a little bit maybe after the show. I'll try and post a better picture. But Earth has this small iron core that is solid metal, iron and nickel. Outside of that is a liquid nickel iron core, and that's the important one. We'll talk about that. Outside of that is this huge mantle, which is molten rock, magma. And then you've got the crust, very, very thin, but that's where life can survive. That's still pretty thick. I say thin, it's about 100, 200 kilometers thick. And so Earth is molten. It's got a lot of heat. That liquid core moves inside it. And all that moving metal does something really amazing. It creates a magnetic field. Earth is a giant magnet. It has a north pole and a south pole. And what that does is that actually protects us from the sun's radiation, right? If we bring in the sun, because why not? We remember how big the sun is. I'm also going to try and move it pretty far away. That's not far enough, but you get the idea. You can see it there. There's our sun. So one of the things that happens is all that sunlight, the sun's giving off a lot of radioactive particles. And that dangerous radiation travels all the way to Earth, 150 million kilometers, but instead of killing us horribly, it doesn't, right? It gets funneled up to the North Pole and the South Pole by this magnetic field. And instead of killing us completely, we get the aurora. We get northern lights and southern lights, the aurora borealis and the aurora australis. That's where those dangerous radioactive particles from the sun can collide with the atmosphere without destroying our DNA, ruining our cell phones, and destroying our electrical grids as well. And so the Earth, like a shield, has this big magnetic field. Mars used to have a magnetic field as well, except for one thing. 250 million years ago, the core, the liquid metal core of Mars, froze. Today, there's no liquid metal core. Mars is a rock, a solid rock. There is iron in the center, but it's not moving. It's not liquid. To make a magnetic field, you need moving charge. You need moving metal, in this case. And because Mars froze, it lost its magnetic field. All that dangerous radiation from the sun collided with the surface of Mars, collided with the beautiful lakes, rivers, and the giant ocean across the northern hemisphere of Mars. And that ocean evaporated into outer space. And today, all that's left is this barren, icy desert. And that is the current fate of Mars. But it is getting warmer. It is getting warmer, right? We are almost done. I'm going to talk a little bit more about Mars, and then we'll say our goodbyes within the next 10 minutes, okay? So Mars lost its magnetic field. It's lost all its water. Let's talk about why Mars still might be a great place for life, though. When Mars had a lot of water, it might have had a lot of ocean life, right? The first life to form on Earth was in the oceans. And so presumably, for a planet in our solar system, Mars maybe had life under the oceans. Now, when that water all disappeared, what did that ocean life do? We don't know. Some of it may still be beneath the surface. Now, I said earlier that the Curiosity rover was the only robot to ever drill into the surface of Mars. And it only drilled a couple of millimeters into the surface, so it's not like it's going to find any life. The next rover, and eventually humans, when we do go to Mars, will be able to dig down a little bit deeper and past maybe 1 to 2 meters of depth where the sun's radiation is causing damage. Below that depth, that would be the place to find life on Mars. Now, when I say life on Mars, I don't mean those little green aliens, right? Not like Marvin the Martian from Bugs Bunny. I'm really dating myself here, but nothing like that, right? I'm talking like little bacteria, tiny little single-celled organisms living underneath the surface of Mars. And they might actually be there. And if there is, that would be pretty fantastic. Not just because it would be life somewhere else, but it would be life in our own solar system in a place other than Earth. Where did it come from? How did it get there? Is it the same life that was born on Earth? Or maybe it was born on Mars first and then traveled to Earth. Maybe life was on Earth first and then traveled to Mars. Maybe life arose independently on these two worlds. That would be pretty stellar. Because that would mean that if life could form on two planets independently, it means that life should be everywhere. Around every star, on every planet. So a couple other fun facts about Mars. Mars has the tallest volcano in the solar system. So we're going to fly around and take a closer look at that. It's called Olympus Mons, or Mount Olympus. We all know the tallest mountain on Earth is Mount Everest. Olympus Mons is 3 times as tall and 10 times as wide as Mount Everest. And I've just got to find it. There it is. There is Mount Olympus right there. This big guy up here. The thing is that Mars doesn't have tectonic plates like the Earth does. And so volcanoes, they literally just keep erupting in one place and getting bigger and bigger and bigger. So I think 4 of the 5 tallest volcanoes on Mars are the 5 tallest mountains in the solar system. And not far from it is this big scar on the surface of Mars. It's called the Mariner Valley. The Valles Marineris. The Mariner Valley is like the Grand Canyon, except it's about 3 times as long, twice as deep, and 4 times as wide as the Grand Canyon on Earth. So it's not just any canyon, it's kind of a super canyon. And yet Mars is this tiny planet. So a really fascinating, interesting thing. I want to see if I can bring up one more thing about Mars, because I want to show you, I'm going to show you another, let's bring up another view of Mars here, a little bit better view. I'm actually going to share, there we go, let's bring this up. Okay, so this is on the NASA website. They've got a really great little view of Mars here. You can kind of see it moves a lot faster than our animation on Universe Sandbox, but you can see there's the Mariner Valley, right? There's Olympus Mons, but we can also see where some of the landers have landed. The Spirit rover, which was part of 2 rovers, Spirit and Opportunity, the Mars exploration rovers. Spirit, I think, stopped working back in 2013, I want to say. Curiosity rover, which is there right now. Well, we didn't need to see that. That's okay. Thanks, NASA. The Curiosity rover in this big crater called the Gale Crater. The InSight lander, which is fairly recent, landed and is drilling down into the surface. One of the earlier landers, Viking 2. The Phoenix lander was a North Pole lander. Where's Opportunity? Yeah, there's Opportunity rover. Pathfinder was the first rover on Mars. So lots of interesting missions that are still, well, they're all still there. They're not going anywhere, right? And that's the thing about Mars, is that maybe in the next 2 decades we'll get to visit. We'll get to actually do all the things that these rovers can't do. And that's kind of the thing about Mars. And just the last thing that I'll bring up myself to say. The thing about Mars is that it's the reason we're doing all this science, the reason we have multiple spacecraft orbiting Mars and multiple rovers on the surface of Mars is so that they can do all the science that human beings can't do. So that when human beings do come to Mars, we can do all the science that's going to be valuable for human beings to do, right? To dig deeper, to analyze samples right away. Things that people can go and do and explore and learn more than any rover could do. But of course, it's a lot harder to get a human being to Mars there and back safely. Now, we are unfortunately out of time, and I could probably talk about Mars for another 20 minutes. And so I think next time we do a stream, I'll continue talking a little bit more about Mars, maybe saying some of the same things as before. Oh, there is one more thing I do want to actually say. Mars has 2 moons. The 2 moons of Mars are called Phobos and Deimos. There's Phobos. We lost it. They're small, right? And there's Deimos. So let's go take a closer look. Phobos and Deimos are literally 2 simple small rocks. They're only a couple dozen kilometers wide. They don't actually look like this. They're jagged. They're not round. But they're small, right? Remember how we were saying Earth's moon was huge compared to Earth? Mars's moons, its 2 moons, are really tiny compared to Mars. And the last thought that I'll leave you with is that the names of Phobos and Deimos, remember Mars is the god of war? Phobos means fear, and Deimos means panic. So what great names for the moons of Mars when you have the god of war to have the sons of Mars are the moons, fear and panic. And that's where we'll leave off today. I want to say thanks a lot for checking us out today. Thanks a lot for the feedback, for the questions, for tuning in. I really appreciate it. This is going to be live on YouTube After we're done the video, in a couple of hours it will be uploaded, so you can always come back and watch anything that you missed, anything that you want to see again. I'm going to keep doing this as long as I possibly can because it's a lot of fun. But I really, really appreciate the questions because that's the part that I really enjoy. I love hearing all of your great questions about anything to do with space, and I am your happy servant to answer all of them. So thanks a lot for checking it out. Please do check out Astronomy in Action on Instagram, Facebook, or Twitter at Astro in Action. When all this pandemic stuff is over, we will go back to doing planetarium shows in real life, and that's where, let me tell you, I really shine. So thanks a lot for checking us out. I hope everybody has a great night, a great weekend. Chances are we'll be back next Tuesday, so stay tuned for episode 6. Have a great night. Thanks for checking us out. Take it easy. Bye.